And today I'm going to talk about one of my favorite problems in cryptography, that of delegating computation. It's based on joint work with Ron Raz and Ron Rothblum. And before actually I go into the problem, let me start with a too brief overview of the evolution of proofs in computer science. It's a really, really beautiful line of work. And then I'm going to start going to the problem I'm interested, that of computation delegation. And I'm kind of going to take you through a path that kind of led us to our result, which is through a concept that was defined in a totally different field, the field of quantum physics. And that's the concept of no signaling strategies. OK, but let's start first with a kind of overview of the evolution of proofs in computer science. And let's actually start with the beginning of mathematical proofs. So mathematical proofs were first considered already in ancient Greece. And Euclid, more than 2,000 years ago, introduced the axiomatic approach to proofs. And Hilbert, in the 19th century, initiated proof theory, which till this day is a well-studied branch in mathematics. And after thousands of years of research on proofs, still this is what a proof looked like. So what's a proof? A prover wants to convince someone that a statement is correct, that a theorem is correct. He writes down the proof on a piece of paper, on a computer. He sends it over to the verifier, and the verifier reads line by line and verifies correctness of the proof. And in computer science, we asked what's the power of such proofs. And in the 70s, Cook-Levin defined the complexity class NP, which is all the languages that have efficiently verifiable proofs for membership in their languages. And one of the most important open problems in complexity theory and theory in large is whether P equals NP or not. So this is kind of all classical proofs. And the way we think about proofs dramatically changed with the seminal work of Goldwasser, Micali, and Rakoff, who introduced the concept of interactive proofs. And interactive proofs were actually introduced with the goal of constructing a zero-knowledge proof. So the goal was cryptographic. The goal was cryptographic. They wanted to come up with zero-knowledge proofs, proofs that reveal no information. And in order to do that, they couldn't do that using classical proof, so they introduced a new proof model, which they called interactive proofs. So what are interactive proofs? As opposed to classical proofs, they now, the prover and verifier talk back and forth, and moreover, the verifier is allowed to toss coins, he's randomized, and it's only required that he rejects incorrect statements or incorrect theorems with very high probability. So there's probability of error that are allowed here. So this is a very interesting concept, which soon deserved, a lot of attention, and it was realized that actually these proofs seem to be much more powerful than the classical proofs. So for example, a canonical example is the chess one, where say I want to convince you that in this game, the black player has a winning strategy. How do I do that classically? So the only way I know how to do it is by showing you, okay, no matter what the white player does, here is a move for the black, such that no matter what player does, here's a move of the black, and so on and so forth, so that I can convince you that in all the bottom places, the black wins. That's too long of a proof. But it was shown that with an interactive proofs, you can have a proof for this, for the fact that the black has a winning strategy, which is very, very efficient. So the verifier runs in very, very short time. Okay? And more generally, there's the celebrated result of Shamir that shows that actually any statement has an interactive proof where the verifier only runs in the space required to do the computation or to compute the validity of the statement classically with a Turing machine. Okay, so the verifier only needs to run in the space. That's what's called the famous IP equal P space result. Okay, so this is great. So look what cryptography did, right? Their goal was to do zero knowledge, but look, they come up with a new proof system that apparently is seems to be much more efficient than the classical one that was used for thousands of years. Okay, but that's not the end of the story. Actually, still with the goal of zero knowledge in mind, then Benno et al. Wanted to construct zero knowledge proofs unconditionally, no cryptographic assumptions. And again, using kind of this bridge, they came up with, they couldn't do with just interactive proofs, so they defined a new model, which is multi-prover interactive proofs, or let's just think of two provers for now. So what is this new model? Now a verifier is talking with two provers, P1 and P2. He sends them some question, query 1, query 2. he gets answers, and based on that, he decides whether to accept or reject. And the only assumption here is that these two provers are not allowed to interact. So they're put in different rooms, and they're not allowed to talk to each other. Okay, so what's the power of these proofs? So again, soon after they introduced, it was shown that actually any classical proof can be made exponentially shorter in this model using a two-prover interactive proof. So if you only had two provers and you can put it in different rooms, the proofs can be really, really short. And the verifier could be very, very efficient. So that's fantastic. And this result led to the following very nice observation by Fortno et al. So what they observed is the following. They said, well, if the proof is so short, so the queries are so short, actually, instead of talking with the provers, so instead of talking to prover one, maybe prover one can write all the answers to each and every possible query in a long, line. So for any query, he writes the answer for query one, answer for query two, and so on and so forth. And the prover two can do the same thing. So now actually, let's forget about the provers. Let's just think of the verifier as having one long string. That's his new proof, and he only needs to read two cells in this proof. Okay, and this kind of idea led to a lot of work that tried to get this proof as short as possible, and the number of bits that the verifier needs to read from this bit as fewer as possible. And this led to the celebrated PCP theorem, or probabilistically checkable proof theorem, that shows that any proof can be converted into a probabilistically checkable one of almost the same size, so there's not too much blow up in size, and the verifier needs to read only a constant number of bits in order to be convinced with some constant probability. And of course, you can amplify by parallel repetition. Okay, so where are we? So this was kind of too brief of an overview of kind of the evolution of proof. So we started with classical proof, with Euclid, and we went to interactive proof, multi-prover interactive proofs, and the PCP proofs. So, now let's kind of fast forward to the problem I'm interested in, and I want to talk to you about, and that's of computation delegation. So what's computation delegation? So in today's world, we have a lot of weak devices, and they need to do some expensive computation, and they want to delegate their computations to the cloud. So let me be a little more details. So we have a weak device, let's say our cell phone, there's the cloud. The cell phone needs to do some computation. Let's say he wants to compute a function f on input x, and he wants the cloud to do the computation for him. So he sends a request, and the cloud does the computation for him. Okay? However, this cloud, he may be malicious, or he may have an incentive to cheat. Maybe the computation requires a lot of, it's a lot of computation, it's expensive, or maybe there's just bugs there, and the weak device really wants to be sure that the computation was done correctly. So he wants a proof of correctness. He wants a proof that proves to him that the computation was done correctly. And here are the two very important issues, the two important properties that we want. First, verifying should be much easier than computing. Okay, so of course, if verifying is as hard as computing, we don't need the cloud. So verifying should be very, very, very efficient. And also, proving should not be too hard. So of course, the cloud needs to do the computation, but we do not want him to work too much more than that. Okay, so these are the two important goals we'll have in mind. The cloud should not have too much overhead, and the weak device should be very, very efficient. Okay? And now these proofs, they can be interactive, they can be non-interactive. We can require statistical soundness, so be sure that no cloud can cheat, or we can require only computational soundness, which says, okay, a cloud cannot cheat unless he runs in like really exponential, super exponential time. Okay. Okay, but the most important thing is verifying super efficient and not too much overhead for the cloud. Okay, so how does this, so I just showed you like very nice work on interactive proof, multi-interactive proofs, all these proof systems, PCPs, can we use them to get our results? So let's see. So classical proofs, that's a bad idea. These are too long. So if you want to show that you did a computation correctly using a classical proof, usually the only way you can do that is just by showing the entire computation. It's just going to be too long. How about using interactive proofs? Well, interactive proofs, it turns out, I didn't say that, but it turns out that the interactive proofs that we had, they have an exponential blow up in the prover's runtime. So the verifier is efficient, he runs in the space, but the prover's runtime, there's an exponential blow up. So that's not good for us. We want the cloud or the prover to not have too much overhead. Okay. How about multi-prover interactive proofs? There, everybody's efficient, actually, so that's great. However, it requires at least two provers that do not interact, and we have only one cloud, okay? And about why not use probabilistically checkable proofs? Well, you only need to check them in a few positions, but this long proof needs to be written somewhere. So again, that's not suitable for us. Okay? Let me just mention, in the regime oops, sorry. No, never mind. In the regime of interactive proofs, we have a result joint with Shafi and Guy Rothblum showing an interactive proof where the proving is not actually much harder than computing, so there's not much overhead. However, this is only for low-depth circuits, for functions that are computable by low-depth circuits, more specifically the runtime of the verifier and the number of rounds they need to communicate depend linearly on this depth. Okay? And the focus of this talk, what we want is a two-message delegation. We don't want interaction back and forth. We just want like one round, two-message delegation, and we want a general result for all functions. Okay, so let me be a little more specific about what exactly we want. So we want the weak device to send, here's what I want you to compute, f, x, and some questions or queries. And the cloud gives the computation, gives the answers. That's it. And let me just mention, the function f and x don't have to be sent. If they're somehow agreed upon ahead of time, great. Okay, you don't have to send them along. Okay, and in the regime of two messages, if we restrict ourselves to two messages, we have to allow for only computational soundness. We cannot hope to get statistical soundness on assuming reasonable assumptions in complexity theory. So we relax our soundness requirement and protect ourselves only against computationally bounded adversaries. And the focus is, we want to get this under standard assumptions. Okay, so this is actually a result. The next slide is going to be my one slide where I have kind of a formal, I was told that every talk should have at least one formal theorem, so that's in the next slide. So I'm just rewriting this result formally, which is our main result. So we show a two-message delegation scheme. We denote it by PV, a proven verifier, such that for any time and any function, any time t, any function computable in time t, we have the following guarantees. So standard completeness, which says for any x, if the prover did the computation correctly and gave f of x, the verifier is going to accept with probability close to 1. Soundness, which says for any x and any cheating prover that runs in time poly t, is the time to do the computation. If he tries to convince the verifier of a wrong statement, so he tries to prove that 1 minus f of x is right, so it's a wrong statement, he's going to be rejected with very high probability. And our result assumes sub-exponential LWE, learning with error. I'm going to get back to this point in a minute. And then the complexity guarantees, our verifier is quasi-linear, so of course he needs to read the input, but not much more. Prover runtime, there's only polynomial overhead. Actually, it's, the polynomial is t squared. And the communication complexity is polylog t. Okay, so very short communication. Let me just mention, the reason we need to rely on sub-exponential hardness assumption is inherent. If you want polylog communication and allow your prover to run in time poly t, you have to end up with sub-exponential assumptions. We can relax the sub-exponential if we allow more communication. So from now on, the talk, I'm just going to say LWE, but actually it's more than, it somewhere lies between sub-exponential and polynomial time, depending on the communication complexity. Actually, let me mention that we don't need to rely only on LWE. We can rely on any computational peer scheme, private information retrieval scheme. Okay, but I'm going to talk. So any peer scheme will do. We know of such peer schemes under different assumptions as well. Okay, so this is the main theorem. But before I go into that, let me kind of give you a brief history of the problem of two-message delegation. And this time, we're not going to go all the way back to ancient Greece, but this starts with Kalai in 1994. So, okay, so there's been a lot of work starting with Kalai on this problem. And the goal of these works was to get, there's been a lot of work. There's been a lot of works trying to get, to solve this problem under standard assumption, better assumptions, and a lot of work trying to solve these things practically, so schemes that actually run efficient in practice. This is only, there's been a lot of work that are not mentioned here. And let me kind of give you a quick state of the art of two-message of the more theoretical type work. I'm not mentioning all the applied work that has been done. I'm going to get to it, though, in a minute. Okay, so the goal was to relax assumptions, to get two-message delegation under the best assumption possible. The starting point was the work of Kalai, which did it in the random oracle model. So we needed to assume random oracles. And then there's been a bunch of work trying to get it under other assumptions that were still non-falsifiable assumptions. So all these assumptions, an example is the knowledge of exponent assumptions. So all these assumptions kind of assumed that the adversary behaves in a certain way. Okay, then there was a work on trying to, two-message delegation, but there was, again, only for depth D. So it's two-message, it wasn't interactive, but it was only the verifier, the verifier's runtime dependent on the depth of the circuit that we're computing. And then there was a bunch of work in the pre-processing model, and these were so the work for depth D was under LWE, which is a standard assumption. The works in the pre-processing model were also under LWE and other standard assumptions. But in the pre-processing model, these works assume that the verifier, the weak device, does need to run once ahead of time a very expensive computation. So it's delegation kind of on average with time. And there were also other caveats to these works as well, which I don't want to go into. But so these works were kind of they were good in the amortized sense. And the last thing I want to mention is that if you allow 4 messages, then we have a great solution of Kilian, which only relies on collision-resistant hashing. Okay, so it's very standard assumption, but required 4 message. And the goal of all these works was trying to get to 2 messages, so we want a non-interactive solution. Okay, so what we show a 2-message delegation for any deterministic computation under the learning with error assumption. Okay? And as we said, we can do it under any computational peer scheme, which can be instantiated under LWE and under other assumptions. But for this talk, actually, just for the sake of simplicity of notations, I'm going to use a bigger hammer, and I'm going to assume we have fully homomorphic encryption, FHE. We don't really need it, but it's easier to show the results using FHEs. Okay, so I'm going to show it. I'm going to, from now on, every time I say FHE, actually a computational peer is good enough. Okay, before we start, let me warn you, this is a theoretical talk. Okay, our result is theoretical. However, I do want to mention that there are quite a bit of work going on that try to implement delegation schemes. Many of them are delegation schemes that started theoretical, and their ideas and techniques have been used to try to make them practical and are being implemented. And I'm going to get back to this point at the end of my talk. Another warning is what I'm going to talk about from now on is going to be oversimplification of the actual result. So those who want the real result are welcome to the 103-page manuscript, which is available online. But it's the result, to get the result, it requires a lot of technicalities, and so I'm going to make it gross oversimplification of it for this talk. Okay, so let's start. So how do we get our 2-message delegation? So we use a totally different approach, a new approach, where we find a connection between the problem of delegation and the concept of no signaling strategies. So no signaling strategies were defined in the mid-'80s by quantum physicists, and they're motivated by Einstein's special relativity theory or by the concept that information cannot travel faster than the speed of light. I know this seems very weird, but now we'll start the path and you'll see where this no signaling comes up. Okay, so we want two-message delegation. The starting point, before that, let me be a little more precise. So the way we do it, a little more precisely, first we show that if we had what's called a no signaling proof, I'll explain what that is later, but if we had that, we can use FHE or peer to convert it to two-message delegation. Okay, so if we had that, we would be done. And then the second thing is we construct such no signaling proofs for any computation. Okay, so these are two steps. More precisely, first we show how to convert. So the theorem 1 says how to convert any no signaling proof, which again, I didn't define what it is yet, how to convert it into a two-message delegation scheme using FHE or peer with essentially the same complexity guarantee. So the runtime of the verifier and prover in the two-message delegation is essentially the same as the runtime in the no signaling proof. Okay? And secondly, we show how to construct a no signaling proof for any t-time computation, which exactly the guarantees we want. So the prover's runtime is only polynomial overhead. Again, it's going to be t squared. Verifier's runtime quasi-linear, and the communication is polylog. Okay, so these two theorems together give us the two-message delegation scheme we want with these guarantees. Okay? So for this talk, we're going to mainly focus on theorem 1. I'm going to say very little on theorem 2 on how to actually construct these no signaling proofs. Proving theorem 2 takes a little more than 70 pages in our paper, so it's very technical. I'm hoping to say a few words on it, but not too much. Okay, but let's start. Okay, so the starting point of our work is multi-prover interactive proofs. Why is that the starting point? Because they're great. We know that using only two provers, we can really get what we want. So the prover's runtime the prover, there's only polynomial overhead, can be brought down to much less by now to like t to the 1 plus epsilon. But anyway, polynomial overhead, very efficient, very small communication, really what we want. Okay, but we don't have two provers. We have one cloud. So what we want is somehow to go from two provers to one prover. And Yael et al. Gave a very beautiful way of doing that. Okay, actually their result was pre-FHE. They said the result, they introduced the result in terms of with peer, but I'm going to write it with FHE because the notations is easier. So what's their idea? Their idea, they said, okay, just send the two queries to one prover. Okay, but if you send them to one prover, it's not going to be secure. So their idea, they said, okay, well, send the queries encrypted. So the hat there stands for an FHE encryption. Okay, so send each query encrypted, and each query will be encrypted with a fresh public key. Okay, the public keys are also sent. I just didn't write them to avoid cluttering of notation. But the verifier, what he does, he encrypts the query 1 with one public key, encrypts query 2 with another public key, both of them fresh public keys, independent, send them to the one prover, and the prover, underneath the layer of the FHE, does the computation, computes the answer. Okay, so computes answer 1 under the public key of Q1, compute answer 2 under the public key of Q2, and sends it back. Okay, the verifier who knows the secret keys decrypts and accepts or rejects exactly when as the verifier in the two-prover case. That was their idea. Now, intuitively, why should this be secure? Let me give you the intuition. Intuitively, suppose there exists a cheating prover who cheats. Okay, proves us an incorrect statement. Okay, well, he cannot cheat by having A1 depend only on Q1 and A2 depend only on Q2, because otherwise he can cheat also in the two-prover case. So if he cheats, one of the answers, let's say answer 2, depends on both Q1 and Q2. You cannot cheat with answer 1 depending only on Q1 and answer 2 depending only on Q2. So suppose A2 depends on both. Well, if A2 depends on Q1, then it has some information about Q1 in it. You can use this information to break the semantic security of the encryption of Q1, because you got some information. their intuition. Okay? However, Dweck et al. Showed that this intuition is misleading. Why? They showed that actually the fact that they depend on each other, the fact that A2 is a function of both Q1 and Q2, does not mean that it has information about Q1. It may depend on Q1, but actually contain no information about Q1. And then you can't use them to break the semantic security of Q1. So the fact that A2 depends as a function on Q1 does not mean that you can use them to break the semantic security of Q1. It may have no information about Q1. Okay, that was really sad news. And at that point, that was published in 2004. I think they realized this much before 2004. And at that point, that was kind of the end of this, in my opinion, very beautiful heuristic. So we really tried to see, is there any crack in this door? Is there any way we can make this heuristic work? And first thing we said, well, suppose it were true. Suppose we could actually claim that if you cheat, the only way to cheat is by having one of the answers, say answer 2, transfer information about query 1. Like really have information. Then we would be done, because you can use the answer to break the semantic security of query 1. If only this were true. So then we thought, you know what? Maybe we can change a little bit the underlying two-prover scheme. In other words, suppose that in the two-prover scheme, you can only cheat by having one of the answers, let's say answer 2, have in it information about Q1. That's the only way you can cheat, by kind of transferring information. If that were the case, in the two-prover, if in the two-prover the only way you can cheat is by having the answers contain information about the other query, then we would be done. Then we say, oh, well, A2 must also, if you can, that's the only way to cheat up there, then this is the only way to cheat down here, and we're done. Okay? It turns out that this idea of transferring information is well studied, very well studied, and actually it's fundamental in the area of quantum physics. And actually it's funny to stand here and talk about this, because this realization of kind of transferring information, we noticed this actually during crypto conference in 2009. Shows you how long I've been thinking about this problem. But at that point we were like, we need MIP that you can prove secure, that it's the only way to break is by transferring information. And at that point, Hanra said, wait, that really reminds me of signaling. In quantum physics, they talk about signaling strategies. Signaling strategies are strategies that transfer information. And that kind of what took us in our journey to physics, and that's what I want to explain next, is what is this no signaling that I talked about, that we started with? Okay, and let me explain what no signaling is in the context of two-prover interactive proofs. Of course, it wasn't defined in this context. It was defined no signaling between particles, but we're going to talk about it in the context of two-prover interactive proofs. Okay, so let's first start with classical strategies. So in classical MIP, multi-prover interactive proofs, we assume cheating provers can have only classical strategies, which means they're not allowed to interact at all, okay? Answer 1 is a function of Q1, answer 2 is a function of Q2. That's it. Is that reasonable to assume? Seems, yes, why not? You put them in different rooms, and it's fine. You know, if you're afraid that they'll talk, put them really far away, put them in different planets, okay? They won't be able to talk. However, quantum physicists may disagree, because they can say, you know, even if you put them in different planets, they can still have entangled quantum states. And so if prover 1 measures his state, it causes a collapse in the state of the other prover, and that may give them additional power to cheat. And indeed, they defined quantum MIPs, which are proofs that are secure also against quantum strategies. So in quantum strategies, again, you're not allowed to talk, but you may have entangled quantum states. Okay. However, the real skeptics, they can say, you know, quantum theory is known to be incomplete. God knows what else they can do using physical means. Maybe there's much more they can do. From what I think they can do anything they want. However, there's one thing I believe they cannot do, and that's talk with their ancestors. Or the only thing I'm willing to believe is that information cannot travel faster than the speed of light. So if they're in different planets, I don't believe they can information can travel from one. They can transfer information from one to the other. Other than that, they can do anything. Okay? So what is no signaling strategies? It says actually the provers can do whatever they want. They can see both queries, do whatever. However, we still tie their hands in one aspect. The only thing we require is that one, say answer one, of course it depends on Q2 and Q1, but once you fix Q1, it does not depend on Q2. It doesn't give any information about the other query conditioned on the query that you see. And same about Q2, about A2. So let me be a little more formal. Again, what's a no signaling strategy? Now the provers can do whatever they want. So they see both queries, they can answer however they want. However, we tie their hand in one respect. A1 sees Q1. Condition on Q1, as a random variable, it's independent of the other query of Q2. So the answer 1 and query 2 are independent. If they were dependent, it means information somehow traveled. And same for the other query. And for the other answer. Answer 2, of course, it's a function of query 2. But conditioned on query 2, if you look at the random variable A2 and query 1, they're independent. If they depended on one another, it means that this information somehow traveled. Okay? So that's no signaling. The no signaling essentially assumes that information cannot travel from one prover to the other. Other than that, they can do whatever, very loosely speaking. Okay, so going back to our goal, well, if we could prove that if we started with a two-prover interactive proof that was secure against no signaling strategies, so the only way to cheat was to signal, was to give information, then we would be done. Then this would be secure, assuming the FHE is secure. Why? Because otherwise, one of the answers must signal information about the other query, or must contain information about the other query. And then you can use it to break semantic security. And we're done. So if we only had no signaling MIP, we would be done. And again, this is oversimplification. It's not enough to have no signaling. We need statistically no signaling. There's a little, some more things there, but this is the gist of it. That's the main idea. Okay, so now, but do we have such no signaling proofs? Okay, so before actually I answer this question about what the state of the art here was, let me first kind of to make sure, to give you some more intuition and make sure we're on the same page. So classical MIPs are more broader than quantum, and no signaling are the smallest. So any no signaling MIP is also secure against quantum attacks and against classical attacks. So if you take any classical MIP, if you have quantum attacks, you may be able to break it. Okay? But even if it's secure against quantum, if you allow any no signaling attack, so now any attack, as long as it doesn't signal, so no signaling is kind of the hardest to get. Okay. Even though it's the hardest to get, let me now show you an example of a classical MIP that's not secure against so I'll give you an example of a classical MIP that I can break without signaling, with a no signaling strategy, just to give you some intuition about this notion. Okay, so I'm going to give you an example why there's not equality, why the yellow circle is not everything. Okay, and the example is an example of Dwok, and that's of 3 coloring. So suppose the provers want to convince the verifier that a graph that they know is 3 colorable. Okay? Here's it's not a good MIP, but it's a proof. Here's the proof. The verifier, what it does, he gives the provers either the same vertex or adjacent vertices. Okay, so the same random vertex or adjacent random vertices. And the provers answer with the color of these vertices. If the verifier gave the same vertex, he'll accept if the colors are the same. And if he gave neighboring vertices, he will accept if the colors are different. And of course, the colors have to be always, red, blue, and green. Okay? So note that with a classical strategy, you can't always cheat. There's some probability you'll be caught. Okay? However, with a no-signaling strategy, you can always cheat. You'll never be caught. And here is a no-signaling strategy that cheats. What you do, what the provers do, they look at the two vertices. If it's the same, they answer with the same random color. If they're adjacent vertices, then they answer with random different colors. The point is that if you look at one color, let's say C1, it's truly random, no matter if it was the same vertices or different vertices. So the color of the answer of one prover, let's say color 1, really signals no information whatsoever about the query, about the vertex of the other player. Okay, so here's a no-signaling strategy that you can always cheat with probability 1, and whereas you cannot do that with a classical strategy. So this kind of just gives you the intuition that coming up with a no-signaling proofs is harder. Okay, so what's known about this? So this was studied by quantum complexity, in the quantum complexity field, and this is what they know. So first they have a lower bound, showing that with no signaling proofs, you can't do more than exp. Languages are computable in exponential time. This is in contrast to classical MIP and quantum MIP, which are known to be equal to NEXP, to non-deterministic exponential time. So they showed that no signaling, you have to restrict yourself to deterministic languages. Okay, and then we have an upper bound that shows that any computation that can be computed by Turing machine running in space S, so it's like the interactive proof IP equal P space theorem, any space S computation does have a no signaling MIP. However, the runtime of the prover is exponential. So we can't use it for the sake of delegation. We want efficient provers. Okay? But they didn't care about efficiency of the provers. So they have a lower bound, it's contained in X, and they have some upper bound that it contains P space or S space computations, and it was unknown kind of where it was. And what we show is that we resolve this question, we show that it's actually equal X, but forget about that. For the context of delegation, this is what we care about. This is what we show. We show that any time t computation, we construct a no signaling proof with the runtime that we want. So the prover runtime is essentially quadratic in the computation time. The verifier runtime is quasi-linear, and the communication is polylog. Okay, and then we can use this in the heuristic we showed before to get the two-message delegation. Okay, so I have time. I'll say a few words about the construction. So you guys still with me? Ready to hear about the construction? So, okay, so here I will have to, really be very, very, very wavy. Note that to construct this is harder than constructing MIP, which on itself is kind of, any MIP is hard to explain. So this is harder. So I'm gonna try to get at just the crux of the points where we had difficulty and give you a little bit of a hint of them. Okay, so let's go. So the construction itself, the initial construction, then it gets more complicated, but the basic idea is just start with standard MIP. Any MIP of your choice, kind of the known MIPs. And let me tell you how they work. So the idea is the following. The provers, each prover, so we have there's some computation F. The prover want to prove that F and X equals 1. They need to prove it. How do they prove it? What do they do? So each one on their own, they generate the tableau of the computation. So this is the tableau. Here are the inputs. You know exactly what the Turing machine would do in the entire computation. This is the time of the computation. We have the space of the computation. Up there is the output bit. Okay, so they each generate this tableau. And then they each encode it. They do some encoding to this tableau. The type of encoding they do, for those who are familiar, it's called low-degree extension coding. For those who don't know, it doesn't matter. There's some encoding. They encode it using some error-correcting code. Okay? And then they expect to be queried on a single point on this encoded tableau. Okay, so each prover is going to be queried on one point, and they give the answer. Okay, that's what they do. What does the verifier do? And this is all similar to classical MIP. Okay, what does the verifier do? The verifier, in oversimplifying, essentially what he does kind of checks he does random consistency checks. So he chooses kind of random locations here on the tableau, and he makes sure that it's consistent. So, you know, all this tableau, it's a bunch of each cell here is an AND of two cells here, or an OR of two cells here. So he takes kind of random 3 cells like that and checks that they're locally consistent. Okay, he does much more than that, but that's the type of things he does. Okay. That's our original idea, exactly like MIP, like classical MIP. Okay, and how does the analysis work? Again, as classical MIP. How do they do it? Well, they show, suppose there's a cheating prover who succeeded, or cheating provers, who succeeded in convincing the verifier to accept, so they pass the random consistency checks. The verifier does random consistency checks, and the provers passed, they succeeded. Then, in the analysis, we show that if random consistency checks passed, then the tableau of each prover must have local consistency everywhere. Okay, it must be local consistency everywhere. Again, this is oversimplifying because the way you read each point is via lines and interpolation and so on, but that's the main idea. The main idea is if you're consistent in random location, then each prover, his tableau, needs to be consistent everywhere locally. And then they show, well, if you have local consistency everywhere, you must be globally consistent. And if you're globally consistent, you're correct. You're consistent everywhere, globally, you're correct. You're done. Okay? That's what they do classically. Okay, now what do we do? Well, this part, going for random consistency to local consistency, to claim that the provers need to be locally consistent everywhere and every single place in the tableau, for this, we actually use very similar techniques to the MIP techniques. So it's these kind of algebraic techniques. But we also have this soundness amplification lemma, which I think is very nice. Unfortunately, I don't have time to show you. But essentially, it says that if we have cheating provers that succeed in cheating with some probability epsilon, then we have provers of a related scheme. But essentially, we have provers that can succeed in cheating with probability, almost 1. Okay, 1 minus, 1 over poly t. So probability very close to 1. So we have this sound amplification lemma, and together with kind of the PCP-like techniques or MIP-like techniques, we managed to go from random to local. Okay. How about from local to global? Okay, so here, in the classical setting for classical MIP, going from local consistency to global consistency is trivial. And I'll show you it in the next slide. That's nothing. All the work is in the first arrow. For us, this part contains all the work. Okay, so on top of doing all the MIP, PCP stuff, we need to work really hard here. And I want to tell you why, and I think explaining, so the next thing I want to show is how classically they go from local consistency to global consistency, and where this approach fails in the no signaling context. Okay, I think it sheds light again on this notion of no signaling. Okay, so what's the goal now? We want to say, suppose the provers, their tableau is locally consistent. Does it mean that it's consistent everywhere? Okay, that's what it means that it's consistent everywhere. And let me prove to you. So going from local to global consistency. Here's the proof. Well, this is the classical proof. Okay, what's the probability? So take one prover. What's the probability that his tableau is globally consistent? So consistent everywhere. Well, it's the probability that local consistency happens everywhere, by definition. What's the probability that local consistency happens everywhere? Well, it's 1 minus the probability that at some point in the tableau, it's not consistent. There's inconsistency. Okay, but then I use a union bound, simple union bound. And the probability that there exists a local inconsistency is the size of the tableau, t times s, times the probability of a local inconsistency, which is epsilon. So if you take epsilon small enough, 1 over t to the third, you're done. Simple union bound. Okay, and that's it. Okay, now this does not work in the no signaling. This proof is, it's not just false, it's not well defined. It's not even clear what this means, and I'll tell you where the problem is. This. What do you mean, what do you mean the probability that you're local consistent everywhere? You look at the prover, his answers depend on the other queries. Right? I mean, now in the no signaling strategy, when the answer to one query depends on the other queries as a function, maybe not as a random variable, but as a function. So it's not even clear what it means to be, you change the other queries, I change my reply. Okay, in the classical setting, you can take one prover and tell him, okay, I ask you this query, what do you answer? I ask you this query, what do you answer? I ask you, and you can reconstruct his entire tableau. In the no signaling case, you can't reconstruct his tableau because it changes depending on the other queries. For a specific query you ask him, well, you ask him with one queries, you get 1. You ask him with another queries, you get 0. So this approach does not work. And this going from local to global is kind of where we need to do a lot of work to make this work.